Windows.
Okay, good afternoon, everybody. It's a real pleasure to have here today Professor Parrondo from Universidad Complutense of Madrid. Professor Parrondo, apart from an old friend of, I would say maybe half or a third of the people here in the audience are former collaborators, people like Raúl and someone else, is a very distinguished scientist now. I'm using words from a recent laudatio in a prize I heard in Dresden. Professor Parrondo was awarded, starting by the end, was recently awarded the Martin Prize by the National Institute for the Physics of Complex Systems in Dresden for his foremost contributions in statistical physics of outside equilibrium systems, including the well-known Parrondo's paradox that probably is known by everybody. Himself has worked on a range of topics from stochastic processes, doing his thesis in the UNED, in the Open University in Madrid, to many topics including ratchets, game theory, paradoxical games, and more recently he's working, some people say, in particle physics, the theory of everything. No, it's not. There are other sides. Juan Parrondo has many sides, and one of the sides that many of you probably know is his monthly column for 7 years or 10 years, I don't know, in Investigación y Ciencia, that is the Spanish translation of Scientific American, where he has been contributing a monthly column on mathematical games, I think it's called. It's more or less a continuation from the former Martin Gardner column. And today will delight us with his recent results on, basically, I understand, extensions of the fluctuation dissipation theorems for non-equilibrium systems in a steady state. Please.
Okay. Thank you very much, Manuel. Thank you to the Institute for inviting me. It's a pleasure to be here in Mallorca, and as Manuel said, with so many friends. I also see a lot of new and young people, so this is a good thing that it's really growing. And I couldn't resist to use this title because it's a little bit pretentious, but well, we will only a little bit. That you will see that this is what we are trying to do. We are trying to develop some theoretical framework which could be applied to almost any system. And well, in fact, it would be, well, I have to say also that this is, I think, of all my talks, this is the talk with more equations. There are more equations that have plots. Sorry for that, but I think the final purpose, or the final goal deserves this, is worth to go through all the maths to achieve the final goal of this linear response theory of everything. And this is what we want to do. We want to take any system, the state of the macroeconomic state of a country, a genetic network, an ecosystem, an active gel, wherever you can think of, and perturb it. We can perturb the economic state of the system by increasing taxes, increasing interest rate. We can change a lot of parameters of the system. And what we want to analyze is the response of the system to this perturbation. And you can imagine perturbations in the genetic network, a network formed by all the genes in the cell or in a living organism. We can use thermal shocks or block genes or whatever. And again, this is a system with many degrees of freedoms, but maybe we perturb only a few parameters, and we want to know, or we want to model the response of the genetic network to this type of perturbation. Also in an ecosystem, you can remove species, introduce species or whatever, or change temperature, or change anything from in the environment. And in an active gel, which is a non-equilibrium system, is formed by polymers, and between the polymers you can have molecular motors, and therefore the properties of the gel are not the properties of an equilibrium system. You can also perturb it by many ways, and all these examples, the idea is if we can really describe the response of these systems. It's a kind of pretentious goal, but the idea is to apply the ideas that we know that have worked in statistical mechanics for almost a century. So in statistical mechanics, we know statistical mechanics has done this job for equilibrium systems. So we have an equilibrium system with many degrees of freedom, like for instance the Brownian particle in fluid, which is the number of degrees of freedom is the position of the particle plus the position of all the molecules in the fluid. And we apply a force to the Brownian particle, and statistical mechanics has developed a theory for this type to describe the response to the Brownian particle, which is the Langevin equation. And it's this strategy consists of finding the correct variable and finding a reduced model, replacing many degrees of freedom by noise. The question is, can we apply this strategy to all this variety of systems? And this is going to be the main topic of my talk. So, as I said before, what in the statistical mechanics, this is something that we know that it has been. I mean, it worked, and it has been working for decades. And let me remind you how can we develop this theory to describe a response. Essentially, for the Brownian particle, for instance, would be the Langevin equation. But how the linear response theory works in statistical mechanics? Okay, we have a Hamiltonian with an equilibrium part and some perturbation, and the perturbation is usually a force acting on some variable of the system. The system has many degrees of freedoms beside this x, and now we perturb the system by this force, which can depend on time, and we ask for the response of the system to this external perturbation, and the first or the easiest way to address it is to, what we know from statistical mechanics is a theory for small external perturbations. We will discuss at the end if this can be extended to arbitrary external perturbations. But in principle, if the external perturbation is small, we can assume that the response is linear in the external perturbation. And this is usually called susceptibility, which has essentially this form. Okay, this is the first step in statistical mechanics to study the response to external perturbations. This is just a definition, but then in equilibrium statistical mechanics we can find a relationship between this susceptibility and the equilibrium correlation of our body, which is the well-known fluctuation-dissipation relation, which relates the susceptibility with the correlations, time correlations of X calculated in equilibrium. So this part of the equation is in equilibrium, and this part, if you like, is out of equilibrium. And temperature appears. So we have this fluctuation-dissipation relation, which allows us to, we don't need really to measure or to calculate the susceptibility. We just need to really characterize or understand very well the equilibrium system. And once we know the equilibrium system, we can go using the fluctuation-dissipation relation to the response to the non-equilibrium part. You can run it whenever you like. And from this type of from this definition and this relationship, this is just a definition. This is a non-trivial result because it is a relationship which is in principle depends on the evolution of the whole system. From these two things, we can derive a reduced model to study the response. And this reduced model usually has this form. For instance, this is in the case of the Langevin of the Brownian particle. This is a Brownian particle. This is X can be written as some big kappa. The velocity of X, the velocity of the particle is proportional to the force. This kappa is of course related with the susceptibility. There is some noise which is related with the correlation, and the fluctuation-dissipation relation, which relates susceptibility and correlation. In the case of the Brownian particle, relates the correlation. Relates the noise with kappa through the temperature. So this is standard statistical mechanics, and we know that this approach or this protocol works with many systems. Not only with the Brownian particle, with Brownian particles and molecular motors and gels actually this is an example of, in general, linear irreversible thermodynamics plus fluctuation. So the idea is if we can, and this has a lot of success in almost 1 century, and the idea is can we extend this, generalize this to non-equilibrium systems? And what I mean, of course, this is non-equilibrium. What I mean non-equilibrium is here, there is non-equilibrium because of this F, but the reference state is equilibrium. So we are perturbing a state in equilibrium, we are perturbing with a small perturbation a state in equilibrium. The idea is how we do the same with the system out of equilibrium. So we have a system out of equilibrium and we perturb it. How we study the response of this system. And when I say a system out of equilibrium, it could be a physical system or it could be a ecological system or whatever, or a genetic network. We don't even need a real Hamiltonian. Okay, so here, using the fluctuation-dissipation relation, we can find a linear model, which is this one, reproducing the actual response and the correlation of X in the system. And this means that by building this model, we have reduced dramatically the number of degrees of freedom of the system. We study only one of these degrees of freedom, which is the most relevant of the response to this curve of symmetry. Okay, so can we do this out of equilibrium? And this is the purpose of the talk. I will tell you that the first two parts is something that we have published. This is a paper with Jack Pro and Joanny, and the first part of the talk I will present the most important results of these papers, and in this task, the first and the second steps are okay. We have generalized the fluctuation-dissipation relation to arbitrary systems, to arbitrary Markovian systems, and this is probably the most interesting part, because for instance you have a system where you are working in the savannah or in ecosystems in the ocean or genetic network, and you want really to describe how to experiment with this perturbation, and you want to construct this reduced linear model. Okay, I think this is the most important part, that this is under construction, and what I'm going to present is very preliminary results, very recent results on this last step, which is constructing the model that describes there. But of course, I think it's this is the most interesting part of the talk. Okay, so let me first go to this paper where we have generalized the fluctuation-dissipation relation for system top. Okay, and the generalization is very general, but of course there are some restrictions, and one of the restrictions is that the system must be Markovian. So we start with an arbitrary Markovian system. This means that a deterministic system is also okay for this there. We start with this system. The system is described by possibly a huge number of degrees of freedom, and we have a set of external parameters. Normally, although I use the same notation for vectors here and here, this has a lot of components. Could be the large number of degrees of freedom, but for the external parameters we have only a few of them, 3, 4, something like that. Okay, so as in equilibrium, the key step to apply the fluctuation-dissipation relation is to have a good description and a good understanding of equilibrium. Here we are going to perturb the stationary state, so we need a good understanding of the equilibrium state, of the stationary state. So we start with some probability, stationary probability, which is defined for fixed values of the parameters. And this stationary probability is this rho, which depends on the parameters and is probability density on the degrees of freedom. And we are going to define a non-equilibrium potential, which is just the logarithm of this probability density. I will show you the theorem, and then we can discuss what is the meaning and what is what could be the how could it be applied to different systems. So we have the logarithm of this probability density. Think, for instance, if this is equilibrium, this will be the Hamiltonian more or less. And then we define something that we will call conjugated variables of the external parameters, which are just the derivatives of the potential with respect to the parameters. You see that we have as many as external parameters, so we have a few degrees of conjugated variables. And these variables will be the relevant variables to describe the response of the system. So we have the first step in the program was find relevant variables. Second, characterize the response, and the third one, build the reduced model.
Here capital X has nothing to do with small x.
This capital X has nothing to do. Actually, this can be 1,000 of degrees of freedom, like in everything there, where you can have 1,000 of them, and here maybe you have two parameters, two genes relevant, and this is so this capital X is there are only a few numbers here, and here there are huge, there are a lot of them.
What is lambda zero?
And lambda zero is the reference state. So this is defined in general for any lambda. But as I said before, we are going to perturb a system which is in a stationary state, and this stationary state is given by a set of parameters which is fixed.
But this is a steady state which is out of equilibrium.
So
So it could be, for example, a laser.
anything.
The steady state of the laser for you is a steady state out of equilibrium.
So the idea is we have a steady state and we perturb it. But the steady state could be even something which is not a physical system, like any dynamical system that you can imagine, or any real system like
The steady state.
economics.
Steady state meaning.
That you have a steady state. Of course, must be stationary. time independent.
No, but you are not, probably you don't mean that the X are stable. You mean that some macroscopic observables are stable.
Yes, the steady state in the statistical, in the probabilistic sense, that all the mean values are independent of time.
Mean values and sample average or time average?
I would say sample well, the system is ergodic in sample average and time average. And I would say that when I said that this is an arbitrary Markov system, why? I don't know, but I think it's better if it's ergodic. Because otherwise, if it's not ergodic, we have several stationary states, and probably we have to apply the theory to different stationary states, possible stationary states. So if it is ergodic, if the Markovian state is ergodic, then you can think of average over a sample or average over time. Okay?
And the only stationary or the stable?
I would say, well, it's, I don't know.
We'll see.
I don't know because, no, I will tell you, I don't know because we have, the proof that we have in the paper comes from another theory. And, and I don't remember what are the hypotheses of this theory. Actually, I remember they don't care so much about stability of the stationary state. So,
But do you
I don't know. I think stability is not enough. It's not important. But of course, for applications, this must be stable because otherwise you cannot perturb. The idea is to perturb a system, a small perturbation, but of course, the small perturbation cannot drive the system out of the system. So in the assumption is that this is unique and stable. Let's say this is the probability distribution. If you fix lambda, this is the probability distribution reached by the system in the infinite time.
Okay. So then I challenge the title of the second.
Okay.
This is
Almost everything.
Almost everything.
And I think must be also Markovian.
No, but I mean
But
non-equilibrium systems which have a unique ergodic stationary stable state.
So was that very
No. What it is important is the stationary state is the reference state. So even if it's not ergodic, we can think, even if a system is not ergodic, you can have several possible states, and you just put the system in one of the states and perturb it, and then everything is fine. Or it's perturbation theory, so it means that you need a reference state, and the reference state in this case is stationary. So it doesn't need to be ergodic, but I think it should be stable, because otherwise any small perturbation drives it around. Fine. Okay, so we have our conjugated variables, which will play an important role. And now let's do the theorem. This is actually, this is not necessary. The definition of this is this in general. So you have, this is not necessary now, and this is just a new variable that depends on the parameters, but it's not completely necessary to evaluate. Okay. So now we start with some fixed values which define our stationary state, and we perturb it by some perturbation which can depend on time. And actually it can be any. This is, of course, it's a linear theory of the perturbation, but the perturbation can depend on time and say that arbitrary dependency on time. Dependence on time. So we start with this system, and we can define as before, susceptibility. In this case, since we have many parameters, we have a susceptibility for each of the parameters, and this is an arbitrary variable. And then what one can prove is this type of fluctuation-dissipation relation. Remember that X is this thing, so this is very similar, we will see, to the fluctuation-dissipation relation in equilibrium. Sorry for the mathematics, but the idea is to this susceptibility is the response of the system. Again, is how my system responds when I perturb it, and this is calculated when there is no perturbation, when there is only a stationary state, and it's a response is equal to a time correlation calculated in the reference state, which is the stationary state. Well, this is the main result of this PRO that I showed before. And it's a kind of a theoretical result. We don't, it's not clear what could be used for, but well, the equilibrium, the equivalent to the equilibrium system has a lot of applications. So our idea is that this will have also a lot of applications in the future. And one of these applications is this reduced models that I'm going to show. Okay, this is the response, and for the proof, of course, I will not present you the proof of this. We have in our paper, we proved this from something called the Hatano-Sasa theorem, which is a theorem which is like the Jarzynski equality, but for non-equilibrium systems. But it can be proved by perturbation theory, and Udo Seiler has done it by perturbation theory. And Thomas and Hagi in their own report in 1982, they almost proved it. And it was instead of there was a kind of two steps between the results that they have in this report and this paper, because it's essentially a perturbation. This is the result of calculation of perturbative calculation. Okay, so this is for any variable. So this is the response of any variable A. It's interesting to see the response of the conjugated variables. In fact, if you see here is a correlation. This expression is telling you that if you put here also the conjugated variables, you will get the set correlation, which is, well, this is a kind of hand-wave assumption, is going to give you the highest response if you put here the same x as here, because you get the set correlation. But I will go to this point later. So if you put here the conjugated variables, then for the conjugated variables you have a response, a susceptibility, and the susceptibility in this case obeys the fluctuation-dissipation relation, where this is the derivative of the set correlation. So now you have that our conjugated variables, how they respond to the perturbation, they respond with this susceptibility, which is the derivative of the correlation, the set correlation. This is calculated in the stationary state. Okay, too abstract for the, too general for the moment. Let's do some, at least relate with the, just to convince you that this is correct, to particularize, but for the equilibrium case. In the equilibrium case, if you have a Hamiltonian like this one, the equilibrium state is the canonical distribution, and the logarithm of the canonical distribution is just the H0, sorry, there should be an H0 here, and an F here. Well, this is the potential, sorry, this should be the whole Hamiltonian plus the logarithm of the partition function. Now, if you calculate the conjugated variable, which is the derivative of this with respect to f, we have xkt, and the derivative of this, of the partition function with respect to f, gives you the mean value of the position at equilibrium. So this is your x, and then if you write the susceptibility of x with respect to the function, to the force f, you get exactly the equilibrium fluctuation dissipation relation. So this is a generalization of it. A particular case of this is the usual fluctuation dissipation relation, which is always. Okay. Okay, so this is the main result of this paper, and just let me tell you, before going to the last part of the talk, let me tell you a couple of ideas which are important in this system, in this result. First, that the theorem is not only a generalization because it can be applied to any stationary state. It's a generalization because it can be applied to any external parameter also. So, for instance, in the case of the equilibrium fluctuation dissipation relation, the external parameter must be always a force, or must appear in the Hamiltonian. Here, the external parameter lambda can be anything, can be intensity of noises or whatever. Any parameter that affects the Markov dynamics, the Markovian dynamics, but it cannot be. It doesn't have to be a parameter in the Hamiltonian. Actually, there are several generalizations of the fluctuation dissipation relations are not as general as this one because of this point here. Many of them start with the Hamiltonian, out of equilibrium, the system out of equilibrium, but with the Hamiltonian and with external parameter appearing in the Hamiltonian. Here, this can be applied to any external parameter. The second thing is that we obtain a fluctuation dissipation relation, but by defining the appropriate conjugated variables. So we can prove this because we have defined the conjugated variables at the very beginning. And I have to say that in some other attempts to generalize or to restore the fluctuation dissipation relation at equilibrium have been based on other strategies, like, for instance, predefining the temperature. This is a typical. This is an aside of the talk, but it's important that in some people try to look. People studying response of a system, of a non-equilibrium system, to external parameters, have tried to apply equilibrium fluctuation dissipation relation with the effective temperature. Remember that this is in equilibrium. In equilibrium, this is response and correlations are, let's say, the ratio between this and this is the temperature. So, out of equilibrium, this is not valid, but we can try to put here an effective temperature, which restores the theory. And this has been done, for instance, in the case. This has been done in spin glasses a lot, and this has been done, for instance, also in biophysics. This is the cells in the ear. They are called the hair bundle, and they are some cells that have the response of these cells to pressure differences or to forces, for external forces, is very important for the hearing. Actually, people here, Victor has worked on here, on this problem. Okay, but this is an active system in the sense that there are motors between these cilia, and the system is out of equilibrium. And there are experiments, for instance, done by Pascal Martin. This is 2001. And they try to define. They measure response, and they measure correlations, and they define effective temperature to restore this relationship. And they found that, for instance, if the cell the cells are alive in the sense that they cut this from a frog and they measure response and fluctuation and spontaneous. They measure response and they measure spontaneous fluctuations. And in the first hour, when the cells are alive, there is a clear deviation from equilibrium. This is the effective temperature. But if you wait for 4 hours or so, the fluctuation dissipation is completely restored because the effective temperature equals the room temperature in this case. So this is the response of an equilibrium system. This is the response of a non-equilibrium system. And this was one of the attempts or not to restore the fluctuation dissipation relation, but to measure how much the system deviates from the equilibrium. And this has been used, as I said, in biophysics, in spin glasses, and in the system. Our idea is different. Our idea is to define what we do is to choose the appropriate variables that we store. Instead of just defining this effective temperature, what our message is, the problem is that here, these x are not the conjugated variables of the force. So for a non-equilibrium system, you have a force, but your conjugated variables are different from, even in the Hamiltonian, it appears as xf, but the non-equilibrium state of the system mixes up x, f, and the rest of variables, and then the conjugated variable is no longer x, it's something else. So this is one of the main ideas of our paper, that you can have a fluctuation dissipation relation, but if you choose the appropriate values of the appropriate variables.
In what sense these appropriate variables are related to? You have a fixed point and you have a direction of which is say several directions in which it is stable, but at different times to reach the fixed point. In which sense these variables might be related to the variables which are the slowest manifold of that fixed point, which is a combination of all the variables that you have, but it's not necessarily the one in which you put the perturbation. So that the way you go back to the system is through the slowest.
This is something that we don't know. Remember, this is something that I would like to remember what is this is the stationary probability, and let's see. Well, and this is. Okay, remember that this is the probability density. This is the stationary state, and this is the conjugated variable. So it has some. Are the directions it's the gradient of the probability density essentially. So probably are the directions where the probability density changes more.
Yeah. So it might be related to the system where the dynamic of system to the direction in which the system
this
goes
very
forward to the.
Okay, so our idea is to choose this x. This is the key point. And let me just show you an example. In a linear system like this one, you have a matrix, some forces, some noises, and you can try to calculate response and fluctuations of x, or in general of any linear transformation of x. If you do this, you consider a linear transformation of x and calculate correlations and response, you get this thing with a lot of matrices, and to restore fluctuation dissipation relation, which means that this must be equal to the derivative of this. When you differentiate this, there is an A here, so the only way is that this is the identity matrix. Okay? it turns out that the only transformation obeying this relationship is just conjugated. So in a linear system, and this is what, well, this is a simple example, but in a linear system, the only variables that really obey a fluctuation dissipation theorem are the conjugated variables. And we can apply this, for instance, for the oscillator, for a very simple linear model of the cells in the ear, and we can see that this divergence in the temperature, in the effective temperature, completely vanishes. I mean, completely disappears if you choose the appropriate value of x. This is a little bit strange because we say, well, if there is a singularity, how can a linear transformation eliminate a singularity? Well, the thing is that there is a singularity in the complex plane. This is I can show you something later. But what is true is that if you take x and as the position of this and the force, you get this effective temperature. There is divergence in the effective temperature, but instead of taking x, you take the appropriate linear transformation, which is this one. Then there is no the fluctuation expression of population is completely fulfilled in all the frequencies.
So in the talk, you said that you will be treating cases where this is out of equilibrium, but it's in a steady state. And now you mentioned this case of the bundle where it's actually an oscillator, so it doesn't have a stationary state.
Well, with noise you can have it. If it's an oscillator, you have noise, then the phase is random, and you can have a limit cycle, but if you have any small amount of noise, it makes the system ergodic, and you can have a stationary. Because suppose you have an ensemble, it's true that it's an oscillator, but suppose that you have an ensemble and some noise, then the phase at some point will be random along the overall ensemble, and then you can plot the histogram, and it's stationary. It's a kind of it's a peak thing around the limit cycle. So yeah, it's possible to do it. Okay, so this is more or less the content of the paper, and but my promise was at the beginning that this could be useful to find reduced models for arbitrary systems, and this is the idea. Our idea is the following: is that you consider any system Markovian, stable, stationary. We are adding some restrictions during the talk, but essentially it's any system with Markovian dynamics, and depending on some external parameters which can be modified. The same setup that we presented at the beginning of the talk. Okay, we have this type of thing. So what can we do? First, we have to find the relevant variables to describe the response, and this is an assumption with a plausible assumption that this X are the directions of highest variation of the probability density and things like that. But we will assume that the response can be described by the conjugated variables. Okay, so our system is going to be described by the conjugated variables, and we want to write a model. How can we write a model? Well, we build a model where the conjugated variables have the same response function and the same correlation matrix and everything. And if you think this is what Langevin did or Einstein did in 1905 for the Langevin part. So the idea is to do the same with any system, and the tool is the general fluctuation relation. And in principle, this is possible. I will show you only a particular example, a particular case, which is when the correlations are exponential. If the correlations are not exponential, we have memory kernels, and it's more involved. But suppose that remember what we have. We have a system. We have some parameters, and we can define the conjugated variables. Now suppose that you measure these things, and you measure this correlation in equilibrium. This is in the stationary state, And then you get a nicely exponential decay. Okay, if this is the case, then I tell you the proof is not very difficult, but I will give you the proof that this model is a linear model. This is capital X. It's a linear model with just a few variables, as many variables as external parameters, and these are external parameters, and we have some noise. And this equation with this intensity of the noise has capital X has the same response and the same correlation as the original system. So we have a model. Maybe we start with a model with 1,000 degrees of freedom. We have this model with 2 degrees of freedom, but this model reproduces correlations and response of the original system. And this is the goal that we wanted to do. So, and look at this, at the intensity of the noise. We have exactly, because the fluctuation-dissipation relation, we have a very similar relation as in the Langevin equation. Let's say the susceptibility, or in this case, this matrix L, which gives you how the system changes due to the force. This is related to the intensity of the noise. So there is really a relationship between fluctuations and, let's say, dissipation or response.
Can you repeat?
You have a system. You perturb it, and you want to construct a model which reproduces correlations and response, and this is the model. And you will say, well, I can do this without the need of the fluctuation-dissipation relation, but actually, what the FDR says is precisely this relationship between the noise intensity and the response coefficient.
I have a philosophical problem here. So you know the correlation of the system. Because of this nice theorem, you can calculate from it the response. So you know the correlation and the response. Then why do you want to build a model having the same correlation and response?
Okay, because you can.
If it only reproduces this, it's a so you have.
No, why don't you want to go beyond that? Why
will you reproduce anything else?
Why we need the Langevin equation? So we can go beyond the Langevin equation in many ways. You can do it locally and couple them. You can try to go in a nonlinear routine. You can do a lot of things. Of course, if you are only interested in the susceptibility, the legal susceptibility is fine. The paper is fine. But I think this is the next step, which can be.
I mean, it would be very nice to replace this by a nonlinear model.
Yeah, I will go.
This is nice extension of the linear equation method. So
this is what we are doing in the Langevin equation all the time. The Langevin equation comes from linear thermodynamics. But at some point we say, well, we can change the force by some nonlinear equation, and we are doing this all the time, and it works. So, of course, we need to apply to specific examples and so on. Okay, so just the only application, I would like to have a lot of applications here, but the only application is the gain equilibrium, but at least you see that this structure is the same that we use in equilibrium. So, suppose you have a Brownian particle in a harmonic potential, then one can prove that the conjugated variable is just the deviation of the position of the particle with respect to the equilibrium position divided by kT. And now you put this here, and you get that the velocity of the particle divided by kT is A divided by kT LF plus the noise, and multiplied by kT you get this thing. And if you now define this as the mobility, kappa, the resulting noise has kT squared, a 2 because of this L plus L. So it's 2 times L kT squared and this is 2kt kappa, which is the Einstein relation. So you see that I want to show you that this protocol applies to the Brownian particle gives you the Langevin equation. So the idea is, well, but now we know that this is general for any system. For any system, Markov and so on, and with exponential decay correlation.
And I'm confused that you reduce the example you have the same number of conjugate variables than variables, not than external variables.
Then external variables.
No, but the number of external parameters is equal to the number of variables.
No. The number of variables is very big.
No, in the examples.
In the examples. Yeah.
No, in the example you only have one variable.
No, here you have the whole degrees of freedom of the system, of the path of anything. Yeah. So you are of course, there are many. We started with a Markovian system, but it can be even a deterministic system, and you can have in a deterministic system you can have correlations because of. This is the case in a Brownian particle in the path. Yeah? Here the system is the whole thing, but you only need this L and this A. That's the only thing you need. Yeah? Which of course is for this you have to measure. You have to measure this part. Okay, you have to measure something. But from just one measurement you can write the model.
So you mean the original system is the Brownian particle plus
the whole thing, and then you say my conjugate variable is x. This is clear because the Hamiltonian is whatever you have minus xf. Then this is my conjugate variable. But then I measure two things, A and L, which comes from the correlation only. And then I can write a model. And the model works. So this is what Einstein did, or Langevin did So, just to summarize the whole thing, what is the recipe? If you have a system, and I encourage you to apply it to anything that you can think you are working on. You find the conjugated variable. Of course, you need really to have a good description of the stationary state, and then you need to know very well this the stationary state. Okay, but one should know the stationary state. Find the conjugated variables by the derivative of this. Calculate or measure these correlations. And if they are exponential, then you have an effective model with this, and with this matrix is given by this. So in principle, you only need to know this rho s and these correlations to really find the effective model. Okay, and addressing the question, Emilio's question of can we go beyond the linear model? Well, this is I just added this point because if you already have the response and the correlation, why you want to build this? Well, you can. This can be good. For instance, if you want to couple different systems, or if you want to try to go a little bit beyond. For instance, in the Langevin equation, we know that sometimes once Langevin derived this type of equation, people came and said, well, this is valid even if the force is not constant. I mean, if the force is not an external parameter, even if the force depends on the state of the system. So this is a kind of heuristic extension of the Langevin equation, but we are using this every day and it works reasonably. So maybe from once one has this type of model, one can go beyond this model by many ways, by adding nonlinear terms. I mean, not adding nonlinear terms, but interpreting this external parameter as depending nonlinearly on the state of the system. So, okay, so this is what it has been a little bit abstract, but I think the final goal is relevant for, and it can have, well, I hope it can have a lot of applications, this idea. So we have presented this fluctuation dissipation theorem and the recipe to build produce models reproducing this fluctuation dissipation relation. It has been the content of the talk, and the open questions or open problems is it good? Can this help really to describe systems in general? So the idea is that you need examples, non-equilibrium, or I'm thinking also on genetic networks and things like that. As I said before, this is really all these part is under construction. So we are it's a work in progress. So we are starting to think of examples. So this is something that maybe people here in the audience can also think of examples to apply this. Another question if this is new. Maybe, in fact, what we are doing is we have a lot of degrees of freedom, and we are finding some effective description of the system, maybe based on slope variables. And maybe we have these conjugated variables and this fluctuation dissipation relation, and then there is a Russian paper from the 60s saying that there is a protocol to really find the relevant description, or maybe it's a principle from polyanalysis or something like that. So we don't know really if all this story can be reduced to something already used. And we have to go beyond exponential decay. This is something that we are doing, and this is not very difficult to do. But we are the linear model that results is a model with memory, and we are also tracking. Another question is if we can go beyond linearity by using this as a starting point and then adding some nonlinear dependency on the forces. Okay.
Thank you very much, Juan. Some months ago when we met in Dresden, you told me, I have already given the last of the paradox, but then later you gave another one, so this one is really different, and I know this is the first one you have told me. So, thank you.
It is not a Russian paper. What do you know about the Martin-Sisson-Rose formalism? No, I mean, PC Martin, E.D. Sisson, and Rose. I mean, I don't know, the question is in which sense this is related or not what you are doing. This was a famous paper in the late 70s on correlation and response in non-equilibrium systems. The first thing they do, if I remember correctly, to describe this thing is to double the number of variables, so to introduce conjugate variables to the variables that you have. And then this was for general non-linear, non-equilibrium systems, and what they write down is sort of field theory Dyson equations in which they relate correlation and response. And the way to relate these things was by introducing these conjugate variables. And that was something that then people used using path integral formulations of non-equilibrium systems by introducing these conjugate variables to what they had. And there was always this idea of response and correlation, but in the non-linear regime.
Okay. So it was non-linear regime.
Well, they start dynamically. So they have a first order differential equation in time non-linear for some variables. Okay. And then to describe correlation and response in the sense of ensemble averages of these things, they double the number of variables introducing conjugate variables. And then they have matrix equations in a sort of coupled Dyson equations. And the examples that they were using that was starting to describe turbulence and that kind of thing. And when you go to the physics report by Thomas and Hangi, I'm sure that they were aware of that and some relation must be there.
Okay. Thomas and Hangi introduced these conjugated variables and the molecular potential, which was in the fashion in the 80s. And
So the idea of doubling the number of variables
Yeah.
to couple correlation and response was in some sense a standard.
But so the idea of the conjugate variables was there. But the theorem, the distribution theorem, as we have written it, is new. I mean, we think we review a lot.
No, I think it would be interesting to see the relation with American. But
I was about to say that we know that it was new. It was new because Hamilton was one of the referees.
but if you wanted enough, that was good.
He told me that he was a referee in a very brief audience. I was a referee. And so
You knew they are recording all this.
He knows, he knows very well all these things. So, and he asked us to have some of these references.
In respect to the question by Pera, he says something, probably those conjugate variables are related to slow and fast variables. I'm not sure of that, but perhaps yes or perhaps not, because they live in a different space. So the dimensionality of this vector is the dimensionality of the parameter space, not of the variable space. So it's not clear to me at all what is the physical meaning of those things. Do you have any examples beyond the Brownian particles to know what are physically those conjugate forces?
No, this is something that we would like to do. And we have tried in a linear case, for instance, what is this? I have tried this part, but I must say that.
I mean, they are the directions in parameter space for which
the
probability change faster.
In the linear case, you have this expression. This is you get u from here. U is a minus 1 sigma, and is this thing. And sigma is the correlation of x. So it's not easy to have an explanation.
The direction in which the probability changes most with the parameter.
This is the only thing that
this
is the gradient. This is the gradient of the rock. So, but we don't have a clear idea of what's in it. Not even in the case.
I have a question. Are there any restrictions on the perturbation functional use and time? There
No.
could be any, for instance,
This actually
something that varies randomly, for instance?
this is sorry. Actually, this is the theorem, and you have the same version in the Fourier space. The Fourier space is similar, and it's valid for any frequency. Of course, these things, the susceptibility, because of causality, must be. This is valid only if t is bigger than t prime.
Yeah, and that's about delta lambda, basically. That would be a
This is arbitrary.
smooth function, or could be, for instance, something random. It changes randomly with time.
Well, maybe must be. Yeah, we perform some integration by parts. So it must be probably. I would say that must be smooth, but maybe. I guess maybe it can be extended. Noisy. Because it's valid for any frequency. So even if you have high frequencies, it's okay. But my feeling is that in the derivation there are some analytical manipulations which need delta lambda to be continuous. But again, I think it can be generalized.
The equilibrium apply is equal to a step function.
Yeah, we can apply the function. I think there is an integration by parts, so. And in the Hatano-Sasa, because we come from Hatano-Sasa, and Hatano-Sasa, remember what are the hypotheses. But I'm sure it can be extended.
So if your theorem is based on this, let's say, complete knowledge of the steady state, right? So can you maybe go the other way around? I mean, suppose experimentally you have a non-equilibrium situation, and you apply a small perturbation. Can you say something about the steady state?
That's a good idea. I don't know.
I mean, suppose that you're both the correlations and the response.
Yeah, of course, this tells you if you can measure. Normally, we think of measuring this, which is a measurement in equilibrium, in a stationary state, and from this getting this. Then maybe from the response you can get the correlation, and this will tell you something about that's a good idea. But normally, it's easier to do the measurement of this quantity and from this obtain this one. I would say. Although the Einstein relation is well, you can measure mobility and
Because sometimes you're interested in the non-equilibrium state.
yeah, this is not equilibrium, but this is more. This is perturbation of non-equilibrium. So it's non-equilibrium. So this is from an experimental point of view, for instance, this is much harder to get. You need to force the system. This is just, for instance, in the case of the motion of these cells, these are just the spontaneous fluctuations of the cells, and for this you need to force them, which is more difficult.
What would be the major difference with the quantum version of this?
Well, for a quantum version, I don't know how one do, because the idea is to apply this to even non-physical systems, I mean to Markovian systems in general. So, but I guess you can derive it for quantum non-equilibrium systems. You can probably derive something. And actually, there must be the literature already, because as I said before, in the literature, in the recent literature, in the last 5 years or so, there are a lot of non-equilibrium fluctuation dissipation theories. Hatano-Sasa have some, Udo Cypher, and many people have written some generalized FDR. But they start with already Hamiltonians and some have quantum versions and so on. The idea here is to start with the Markov system in general. And I don't know if for a quantum system you need a Hamiltonian. You go back to the Hamiltonian form.
No more questions? I have one question. Think about the following situation. I mean, you're in a steady state in a non-equilibrium system, and you are in a perimeter region in which you are, I mean, deterministically you are relatively close to some bifurcation, let's say to a Hopf bifurcation. I mean, but you are on the stationary side. Then you have noise. I mean, so you may even have some kind of noisy precursors and funny things. What do you expect to see from the point of view of the theory? I mean, there should be some breaking or some funny things, or would it distinguish that you are close into a point beyond which things are no longer valid? And for hearing, I mean, this could be also useful. I don't know.
Yeah, I think this is on the contrary. For instance, in the case of this can be modeled as a Hopf oscillator, and actually this divergency comes from a natural frequency. I didn't explain this in detail, but this is the Fourier version of this has it's in the frequency domain, and this effective temperature is the same for each frequency, and this divergence is related with not with the Hopf bifurcation, because this system is But even if it's below bifurcation, I think, and still you have some.
Yeah, this is below the.
This is below Hopf, but it has some signature of the frequency of the Hopf.
This is exactly the case that the.
Okay.
And we have, and for a very simple linear model of this, not a real Hopf, just the oscillator, the stable node to an unstable node in the bifurcation. You can. This is a linear case. This is a particular case of this, and all this frequency divergence disappears because, of course, the theorem applies. So even in this case,
but as you come closer and closer and closer to bifurcation, something funny should happen, or not?
That linear response breaks down.
Sorry?
Linear response breaks down.
well, no, linear response breaks down because. Well, touching about the bifurcation it breaks out.
Close to the bifurcation.
Close the version with noise.
Close bifurcation, I don't know. Because for instance, all this part, all this is if I remember, these theoretical curves are in a linear mode.
And that's very close to the.
Yeah, this is very close to bifurcation.
So that's why there is no question, sir.
The singularity of the response is captured by the linear model because the linear model is only capturing what.
The linear model captures the singularity of the response. It's just that the model is not singular.
Yeah, even though.
So the singularity is the signature of the breakdown of the linear response.
And in our case, we restore it because this will be again a curve. So even in our case, with these conjugated variables, probably there will be less information in this respect. But that's another interesting question.
Okay.
I thought it's a very clever system. Like Max started to stop it's manual.
I think tú ves a in the sense of
que la idea de que la gente respuesta a un punto y que para tener unas variables conjugadas ha hecho
makes a lot of noise. You have to calm down. Nina is there. This is the first time.
El único ejemplo que ha puesto que